I'm going to be kind of facing it that way, so if I don't see you, kind of just shout it out or something, and I'll make sure to get it. Okay? Can you hear me fine over there? Yeah? Okay, perfect. So the ACS has its own formula sheet, I guess, or reference sheet, and this is what it looks like. So on top it has different variables, then it has 3 equations that you don't really use very often, and then the periodic table. And obviously the periodic table doesn't have the names, it just has the element symbols, okay? So this is what you get, and then this is really all you need for the ACS. And it gives you constants. So most of the constants that you had to memorize, they do give you, but they don't give you certain conversions, and they obviously don't give you like metric conversions. So these are things that you kind of want to know on your own. So let's begin. So the questions I have on here are from actual past ACS exams, and they're all available to you online. So if you Google past ACS exams, you'll find them, the whole thing. But not everything on the actual ACS pertains to Chem 1. Some of it is Chem 2. Some of it even goes a little bit into Orgo, but not really. So these are the ones that really I thought were Chem 1 related. And actually 2 of the questions on here we're going to not go through because they're not very relatable. So let's start. Any questions? Everyone here for Chem 1, right? Just making sure. Okay, awesome. So I'm going to kind of solve on separate sheets of paper here. So the first question says glycoxal consists of 41.4% carbon. So as you go through the question, kind of underline the different numbers they give you, just so you're aware of what you're working with here. So you have 41.4% carbon, 3.5% hydrogen, and 55.1% oxygen by mass. Anytime it says percent by mass, you're going to assume that you have 100 grams. Yes, sir?
Sorry, where can we find those questions?
You can find them on, if you Google Study Union WordPress, UCF Study Union WordPress, you should get a website, and then if you click chemistry and then scroll down to Laura, you'll find a practice exam. Laura, my name? Laura. You got it? Almost. You got it? Okay, awesome. Of course. So anytime it says percent by mass, you're going to assume that you have 100 grams. And that these percents are of the 100 grams. So that 41.4% is 41.4 grams of carbon, 3.5 grams of hydrogen, and 55.1 grams of oxygen. Okay? And now it's asking for the empirical formula. So as you know, the empirical formula is the one that is the most simplified. So how do we figure this one out? So basically, the first step is always to convert from grams to moles, because we're always going to have to work with the moles, and that's how we figure out the empirical formula. Because it's going to come out to be something like this, CXHYOZ. And now we're trying to figure out X, Y, and Z. Okay? So the 41.4 grams carbon, you're going to multiply it by the molar mass of carbon, which is 12. The 3.5 grams hydrogen, you're going to multiply by the 1.008 grams hydrogen, and the 55.1 grams oxygen, you're going to multiply by 16 grams. Sometimes you can round, it's fine. And then the numbers you get from there are going to be always in moles, because the grams are going to cancel out, right? So 41.4 divided by 12 is 3.45. The 3.5 divided by 1 is about 3.47. And the 55.1 divided by 16 is also 3.4 moles, approximately. So as you can see, they're all approximately 3.4, 3.5. So all of them are around the same. So what happens is, you know that you have C 3.45. So this is because it's always the X, Y, and Z are going to be the moles, right? So you have C 3.45, H 3.47, O 3.4. You're going to find the least common denominator and divide all of them by it. So all of them are approximately 3.4. So if you divide all of them by 3.4, they all come down to be about 1. They all cancel out. So you have C1, H1, O1, which gives you the answer A. So A is my empirical formula. So again, the empirical formula is the one that is the most simplified. So A becomes your answer for that one. Okay?
So for this one, like they were all really similar, so I see why you divided it by 3.4, but in the case of it being like different sizes, which one do you go off of, the larger one or the smaller one?
You go with the smallest, because it can end up being something like this one, CH2O2, right? So you always go with the smallest number that you can, because that's the common denominator for all of them. And sometimes you'll get decimals like 3.1 is 3, right? So things like that you can always round to the nearest whole number, because it always has to be a whole number, right? Okay, that is that one. Number 2. So how many hydroxide ions are in 2.5 moles MgOH2? So hydroxide ions, as you know, is basically OH minus. So you're looking at how many ions are in, how many hydroxide ions are in this compound that we have right here. So anytime it says ions, atoms, molecules, you're always going to use Avogadro's number in a way. So in this one, you automatically know you're going to use Avogadro's number. That's why all the exponents have times 10 to a big power. So you're going to use Avogadro's constant, or Avogadro's number, which is, as you know, 6.022 times 10 to the 23, right? So you already have it in moles. Because it's MgOH2, the 2 goes into the OH. That means I have 2 moles of OH in every 1 mole of MgOH2. So 2 moles OH in every 1 mole MgOH2. And how did I get that? I got that from the actual the formula, right? So that means I have 1 Mg in every 1 mole MgOH2, and I have 2 OH in every MgOH2, right? Because that 2, when the OH is in parentheses, means that the OH, like the whole hydroxide ion, there's 2 of them. So now I know basically the mole-to-mole ratio. So I have 2 moles. So I have 2.5 moles of the whole thing. So now I want to figure out, okay, how many moles of OH do I have? So 2.5 moles of MgOH2 times the ratio that we said right here, the mole-to-mole ratio, which is 1 or 2 moles OH in every 1 mole MgOH2. So the mole MgOH2 cancels out with the mole MgOH2, and I'm given 5 moles OH, right? 2.5 times 2. So now I want to use this and get it into ions. So 5 moles OH times 1 mole OH has Avogadro's number, which is 6.022 times 10 to the 23 ions. Again, the main thing about stoichiometry problems is that the bottom and the top and the bottom always have to cancel. That's how you know you're working on the right track. So the top here cancels with the bottom here, mole OH and mole OH. So now you're multiplying 5 by 6.022 times 10 to the 23, which gives you 30.11 times 10 to the 23. But since none of the answers here match 30, because it's scientific notation, and scientific notation is just one number, I have to move this decimal point back 1. So anytime I move this decimal point back 1, I'm going to increase the exponent. So it's really as if I'm saying 3.0 times 10 to the 24 ions, OH ions. So D is my answer. So again, anytime I move the decimal point back to make it scientific notation, I add an exponent to, I add 1 to the exponent. So that's why it became, instead of 10 to the 23, it became 10 to the 24. Right? Yes, ma'am? It's, so if you Google UCF WordPress, or Study Union, excuse me, UCF Study Union, you should get like a WordPress website and then click chemistry and then scroll down to my name, which is Laura. Laura. Oh, zoom in? Sure. Is this better? Awesome. All right, number 3. So it says if in a sample containing 1 mole of NaBr and 0.3 moles Ki, what is the mass percent of iodine? So you have 1 mole NaBr and 0.3 moles Ki, and that's all in one sample. And it's asking you for the percent of iodine. So iodine here is obviously I. And in this sample, so you have 1 mole NaBr plus 0.3 mole Ki. So because you have 0.3 mole Ki, you're going to look at the Ki only right now. So 0.3 mole Ki, right, has 1 mole I in each Ki, similar to what we did last time. So you have 1 mole Ki, 1 mole I per 1 mole Ki, which means I have 0.3 moles I within it, because these cancel out. So 0.3 moles I want to convert that to grams, because it's always looking for mass percent. So 0.3 moles I times 1 mole I, and I is 126.9 grams I. So 126.9 times 0.3 gives you 38.07 grams I. If we look at how many grams Ki I have, I'm going to go 0.3 moles Ki, convert it to grams. So 1 mole Ki is going to have both K and I added together. So so that's the molar mass of Ki. So 126.9 plus K, which is 39. So 165.9 grams. So 0.3 times 165.9 gives you 49.77 grams Ki. But again, the sample consisted of NaBr and Ki. So I have to also find the molar mass of NaBr. So I have 1 mole NaBr, and I need to convert that to grams NaBr. So I'm going to do the same thing. 1 mole NaBr, and the molar mass of NaBr is 79.9 plus 22.98, or 23. So 102.9 grams NaBr. So I also have 102.9 grams NaBr because it's 1 mole. It's a 1-to-1 ratio. So with that, the total sample mass is the 102.9 plus the 49.77, which I got from here and from here, from converting the overall to grams. And this gives me 152.67 grams. So that's my total. And then we said that the grams of iodine that I have is 38.07. So the percent by mass means of iodine means that I'm going to say iodine over total times 100. And we said iodine was 38.07 grams, and the total was 152.67 grams, and we're going to multiply that by 100. So 38.07 divided by 152.67 gives you 0.249, and we multiply that by 100. So it's 24.9%. And that will be answer A, if you go up here. So it's a little long, but it's not that bad. You're looking at percent by mass, or the mass percent. So all you have to do is figure out, well, what is the mass of I that I have? And yes, ma'am. Excuse me? Grams of I is included in the total because you used Ki. You used the mass of, you used the moles of Ki, converted them to grams of Ki. Used the moles of NaBr, converted them to grams of NaBr to figure out the total mass of the sample that you have. Because it said that the sample had 1 mole NaBr and 0.3 mole Ki. So you have to figure out, well, what's the mass of the whole thing? So you convert each of them separately to grams and then add them up together. That's the total. But I is only present in one of them, in the Ki. So you want to figure out, well, how much I do I have in grams? What? Oh, okay. But that's what you did. That's what you do. And then you figure out grams of I, put it over the total, and and then you figure out, well, what's the percent by mass? Okay? Makes sense? So it would be a 24.9. Okay. So question number 4 kind of runs into the next page, so I'm going to put it like that. So it says barium chloride reacts with sodium sulfate according to the following equation. You have BaCl2 plus Na2SO4 gives you BaSO4 solid, and NaCl, which is aqueous. And then the student mixes a solution containing this amount of BaCl2. When it gives you M, big M equals this, that means molar mass. So they don't want you to calculate molar mass, they give it to you, which is really nice. And it gives you the solution containing this amount of Na2SO4, again gives you molar mass. And it obtains this. So it's asking for the percent yield. The main thing it's asking for is percent yield. So what I would do in solving a question like that is take out all the information they give me and kind of list it down. So they tell you, the equation is BaCl2 aqueous plus Na2SO4 aqueous gives you BaSO4 solid plus 2 NaCl aqueous. Oops. Aqueous. Okay? And it's telling you that you're given 10 grams BaCl2, and the molar mass is 208.2 moles per grams per mole. You are also given 10 grams Na2SO4, and the molar mass is 142.1. And theoretically, so again, with percent yield, you're looking at experimental versus theoretical. So experimental or actual is what, when you perform the experiment, what you actually got. So this is what, if you were to do it in a lab, this is what you would get. So the experimental or actual value they got, they gave you. They have to give you the actual. Because what you're going to find is the theoretical. Theoretical means the one that you would get based on calculations. So you are looking first to figure out percent mass. You have to look for the theoretical. And then they give you the actual. So the actual is 12.0 grams of BaSO4. That's what you actually got in the experiment. But you want to figure out what you got theoretically to figure out percent mass. Percent yield. And percent yield is always actual over theoretical times 100. So you want to compare what you actually got in the experiment versus what you were supposed to get based on calculations. So for that one, you're going to have to compare apples to apples. So because they give you that you actually got 12 grams of BaSO4, you want to figure out, well, what would you have theoretically gotten for BaSO4? So based on this equation, you have two things. You have two reagents, BaCl2 and Na2SO4. So you want to figure out, step number one, you have to figure out, well, what is the limiting reagent? Right? Because the limiting reagent is going to give you the actual, is going to give you the theoretical yield. Because that's the maximum amount you can make based on the material you have. It's like baking a cake. You only have 2 cups of flour. That means even if you have 1,000,000 eggs, you can only make a cake that uses 2 cups of flour, right? So it's the minimum, it's the maximum amount you can make based on the ingredients you have. So you have to figure out limiting reagent first. So to figure out limiting reagent, you're going to use the mass of both reagents and see which one yields the least, basically. So 10 grams BaCl2. You want to figure out, well, how many moles of BaSO4 I can make, or how many grams. I would do either is fine, but I would do moles in the beginning, just so we can compare. So 10 grams BaCl2, they give you the molar mass, nice of them. So 1 to 208.2 grams per 1 mole. And then I like to write it all in one, but to this part, we're finding out how many moles of BaCl2. Now I can figure out how many moles of BaSO4 I can get. Because here in the equation, it's a 1-to-1 ratio, and then here too. So I have 1 BaCl2 reacts with 1 Na2SO4, gives me 1 BaSO4 and 2 NaCl. But again, I'm only comparing BaSO4 because that's what the question is kind of asking for. So now I have that 1 mole. So this is 1 mole BaCl2. Now I have 1 mole BaSO4 can be yielded from 1 mole BaCl2. So I can figure out moles BaSO4. So this cancels out with this. This cancels out with this. So 10. So you're going to multiply all the top and divide by all the bottom. So 10 times 1 divided by 208.2. So 0, I'm going to write it down here. It's equal to 0.048 moles BaSO4. That's how much BaSO4 I can yield from the BaCl2, from reagent number 1. So now I have to figure out, well, how much I can yield from reagent number 2. So reagent number 2 is Na2SO4, and again, I'm also given 10 grams of Na2SO4 times, again, 1 mole Na2SO4 over the 142.1 grams. And then that's the molar mass that they gave me. So again, I'm going to do the same thing. It's a 1-to-1 ratio. So I'm going to do 1 mole BaSO4 over 1 mole Na2SO4. 142.1. So the 10, so this again cancels out with this, and this cancels out with this. So 10 divided by 142.1, and that gives me 0.070 moles BaSO4. So from the 10 grams Na2SO4, I can get 0.07 moles of the product BaSO4. From 10 grams BaCl2, I can get 0.048 moles BaSO4. So the first reagent yields less. That means, since it yields the least, that means that's the limiting. So that means BaCl2 is my limiting. So that's what I'm going to use as my comparing factor. So now I have 0.048 moles BaSO4 maximum to be made from the reagents I have. So I have to convert that to grams in order to compare it with my experimental or actual value to figure out what the percent yield is going to be. So I'm going to use the 0.048 moles BaSO4, and then they give me the molar mass of BaSO4, which is 233.2 grams per mole. So 1 mole BaSO4, and it's 233.2 grams. So again, this cancels out with this, and the 0.048 times 233.2 gives me 11.19 grams BaSO4. And that is my theoretical or calculated value. So that's my theoretical. And so I have the actual from the beginning, which is the 12.9. And I just calculated the theoretical using limiting reagent. So now I want to figure out what the percent yield is based on this equation right here. So the equation is, for percent yield, is actual over theoretical. And anytime you see the word percent, you always multiply by 100. So actual is 12.0 grams, and the theoretical is 11.19 grams. It's okay if the actual is greater than the theoretical. Also, sometimes it can be less. That's why we're comparing it. So 12 times 100, sorry. So 12 divided by 11.19 times 100 gives you 107.23. And according to my questions, that would be, or according to my answer choices, I have 60, 73.1, 93.3. So this kind of trips you off, like, oh, I got a number bigger than 100, so I probably did something wrong. But then you read answer D, which says the isolated barium sulfate is most likely wet since the yield would otherwise be greater than 100%, which is our answer. So because we got, so even though all the answer choices were less than 100, which probably will trick you, it's not. It's greater. The answer is D, which says that it's greater than 100. Okay? So D would be your answer. So this was kind of a longer type of problem, but it's not that bad. All you need to know is that you're calculating theoretical yield, and you calculate theoretical yield based on limiting reagent. Then you do actual over theoretical times 100 to find percent yield. Okay? So that is number 4. Okay, I'm going to try to work a little faster because it's only been 30 minutes. Okay, number 5. It says a white ionic solid is dissolved in water. Addition of a solution of sodium chloride to this solution results in a white precipitate. What was the cation in the original ionic solid? So anytime you see the word precipitate, always think solubility rules. So some of you had to memorize it, some of you had kind of a reference sheet, but with solubility rules, most of the time, it's something that has to do with, so you already know that anything that is group 1 is soluble, so Na cannot work, right? And if you remember solubility rules, the one exception to things, so it says it's a sodium chloride, so NaCl. plus something will give you something that is solid, which precipitates. So it's something that is not in the Na. So this one is eliminated. And usually in solubility rules, the thing that precipitates usually has an Ag in it. So Ag becomes your answer. So this one is kind of based on what you know from previous solubility rules, is that always Ag is an exception. So Ag is usually an exception with everything soluble. It's also in the rules. So Ag would be your answer right here. Okay. 6. 0.1 molar solution of which salt is the most basic. So what I think you guys need to do is memorize the acidic, the strong acids and bases. Strong acids, there's the list. Strong bases, the best way to memorize them is that most strong bases are OH, and the thing before the OH is either group 1 or group 2, so NaOH, KOH, things like that. So in here it's a salt. So because it's a salt, it's not going to be the same way, but it's going to have to have kind of an OH in it. So the first one doesn't have H's at all, so you can kind of eliminate it. So it's going to basically be as if I'm saying NaCl plus a salt gives you Na something, and this is the base. This is a strong base. So the Na is going to be the beginning part. So the answer here is actually going to be D, NaHCO3. And the way you can know that one is, again, memorizing strong bases, because that one, like, you wouldn't be able to figure out just by using, like, you can't just use the periodic table and kind of figure it out. So you have to kind of memorize strong acids and strong bases, because there's a few questions that will ask you, like, strong acids, strong, probably 1 or 2, so if you want to just, not memorize it, it's not worth it that much. But this one, you just have to memorize strong acids and strong bases, okay? So it's D. Number 7. It says a sample of neon gas held at 25 degrees Celsius and 1 atmospheric pressure in a cylinder with a movable piston. Under these conditions, the gas occupies 5 liters. What volume does gas occupy at 12 degrees Celsius and what atmospheric pressure? So these are the last chapter that you guys went over, which is chapter 5, the one about gases. So the equation, so the trick is to figure out which equation am I going to use. So you want to figure out what variables do you have. So you have temperature, you have pressure, and you have volume. Well, which equation has all 3 of them? How about this one? P1 V1 over T1 is equal to P2 V2 over T2. And because they give you 2 conditions with 1 missing variable, you know that you're going to have to do P1 V1 over T1 is equal to P2 V2 over T2. So they give you basically T1 at 25 degrees Celsius, and they give you T2 at 12.5 degrees Celsius. They give you V1 at 5 liters. They need V2 because it says what volume. So we're solving for V2. And they give you P1 at 1 atmospheric pressure and P2 also at 1 atmospheric pressure. So you have 2 conditions with 1 missing variable. So this is what you do. You're solving for V2. So what you can do is alter the equation where V2 is what you're solving for. So you have P1 V1 over T1 is equal to P2 V2 over T2. So you want to get V2 on its own. So first step is to multiply by T2 on both sides. This cancels out. So T2 P1 V1 over T1 is equal to P2 V2. You want to get rid of P2, you divide. So this cancels out. So V2 is equal to T2 P1 V1 over P2 T1. And now all you can do is plug in these numbers, and then you get V2 on it. You'll solve for V2. Also, because this is the gas laws, always convert degrees Celsius to Kelvin. And anything has to be in liters and atmospheric pressure. So to convert anything from degrees Celsius to Kelvin, degrees Celsius plus 273 is Kelvin. So T2 is going to be 12.5 plus 273, which is 285.5 times P1, which is 1, times V1, which is 5 liters, over P2, which is 1, and T1, which is 25 plus 273, 298. Okay, so all the top multiply, divide by all the bottom. So 285.5 times 5 divided by 298. And V2 is going to equal to 4.79 liters, which is approximately 4.8 liters as seen by answer B. Okay. Awesome. Question 8. A sample of 54 grams of methanol is heated from 25 degrees Celsius to 35 degrees Celsius. So that means that TF is 35 and TI is 25. How much heat is required? The specific heat capacity of methanol is this. So heat is going to be Q, right? So we're going to use the equation Q equals MCAT, right? Because I see that I have TF and TI, that means I have a delta T. It gives you specific heat, which is C, and it gives you a mass, which is M, so Q equals MCAT is the equation I'm going to have to use here, because this is the M. So Q is the heat I'm trying to find. I have 54 grams. C is 2.48 joules per gram Kelvin. And the delta T is going to be 35 minus 25, which is 10. So 10 times 2.48 times 54. So 54 times 2.48 times 10 is equal to 1339.2 joules, which is approximately answer number C. Just some rounding. So it's almost 1340. So C is the answer. Yes, ma'am? It's not going to matter at this point because it's a delta, and because they're both going to be added plus 273. You could. It's not going to make any difference, though, because it's a delta, so it's basically a relativity factor. Okay? But good catch, because it does say Kelvin. Okay. How are we doing so far? Good? Comfortable? A little? Awesome. Awesome, awesome. Number 9. That's a long one. That one is going to be Hess's Law. So let's see. So it says, given the standard enthalpy changes for the reactions, and then it gives you 2 reactions, calculate the standard enthalpy change for the following reaction, and it gives you the overall. Calculate the standard enthalpy change for the following reaction. So it's again asking for Hess's Law. So this is Hess's Law. So Hess's Law is basically you are going to manipulate the 2 reactions that they give you to match the whole reaction at the bottom. And then when you manipulate it, you're going to manipulate the delta H's that are here Then you're going to end up adding the equations and add the delta H's to give you the overall delta H of the reaction, which is what you're solving for. So here, in the overall is what you're comparing everything to. So you have P4O6 solid on the reagent side here. That means when you manipulate the equations, you need to have one P4O6 molecule on the reagent side. As you see, in the first equation here, it's after the arrow, which means it's a product. So I want to make it on the reagent side. I want to flip the equation. So in order for me to flip the equation, I multiply the whole thing by -1. That -1 flips the whole thing. So I end up seeing something like this. P4O6 gives you P4 solid plus 3O2 gas. And since I multiply it by -1, this right here becomes delta H is equal to 1640 kilojoules per mole. So it becomes positive, because a negative times a negative is positive, right? Okay, the second thing I have is I have 2O2. Well, I have 3 O2s on one product side, and I have 5 O2s on one reagent side. So again, we said that we're going to add them up at the end. When we add them up, things that are on the opposite side are going to cancel out or simplify. So what ends up happening is that supposedly what happens is when you add these two, things that are in the overall equation are going to end up on the overall equation, and things that were not are going to cancel out. So you have 5O2 here, and you have 3O2 here. If you were to cancel them out, which means you subtract them, right? It's going to be 5 minus 3, which is 2. So it gives you the 2 that you have here. Another way of seeing that this is going to remain as is and you're not manipulating it is that the P4O10 is on the product side, and here it's also on the product side. So you're going to have to keep it as it is. So if you end up adding both equations up, you're going to have P4 here on the reagent side and a P4 on the product side. So because one is on one side of the arrow, one's on the reagent, and one's on the product of the opposite, they cancel out. The 5O2 that I have here and the 3O2, it's going to cancel the 3O2 out, and 5 minus 3 gives you 2. So I'm left with 2O2. The P4O6 remains because it's what I have here, so I'm going to have P4O6. I'm going to have the 2O2. And what I'm left with on the other side is the P4O10. That's just the way that I verify that what I did with the manipulation gives me the correct overall equation, is that you add them up, things cancel out, and things are going to remain. And the things that remain are things that should 100% match the overall equation. So now, I have a delta H that is negative 2940 and a delta H that is positive 1640. Because we added the two equations, I also add the delta H's, and that gives me the overall delta H of the reaction. So it's the positive 1640 plus the negative 2940. And that gives me delta H of the reaction, which is 1640 minus 2940. Gives me a negative 1300 kilojoules, which is B, because it's negative 1.3 times 10 to the third, which is negative, if I move the decimal point 123 times, it's negative 1300. So it's going to be B as my answer. Okay. Question 10, how many total orbitals are there with principal quantum number n equals 4? So, if you remember, we have n, l, ml, and ms. N is the shell, and it's basically, if you look at a periodic table, it's the period number. Period is the one that goes horizontal like that. L is going to be the subshell, and it's the one that can go from 0 all the way to n minus 1. Ml is the orbitals, and it can go from negative L to positive L. And Ms is the spin, and it can only be either a positive half or a negative half. So when it's asking for how many total orbitals we can have in n equals 4, that means it's looking for Ml, because Ml is orbitals. So the way you figure this one out is, because n equals 4, and L can be from 0 to n minus 1. That means L can be 0, 1, 2, or 3. Ml, if I assume it can be any number, or if I choose any L to be my standard for Ml, choose the largest number. So I'm going to choose the 3, because I want to figure out how many total orbitals I can have in that thing, so the maximum number. So I have 3. If I go from negative 3 to positive 3, I have negative 3, negative 2, negative 1, 0, 1, 2, and 3. So I have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7 in the largest number. In the second largest, which is, let's say, 2. So this is assuming I have if I have subshell 3. If I have subshell 2, I have to basically add all the orbitals I can have in each subshell. So subshell 3 has 7. So 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. In 2, I have negative 2, negative 1, 0, 1, 2. 1, 2, 3, 4, 5. In 1, I have negative 1, 0, and 1. That's 3. And in 0, I just have 0, which is 1. So now I have 7 plus 5 plus 3 plus 1. So 4 plus 5 is 9, plus 7, that's equal to 16. So that means I can have up to 16 orbitals in that thing. Perfect. That's easier. Thank you. But just in case you forget, square n. That's just that way I process it to also explain. But n squared is a lot easier, less time consuming. So square n, okay? Awesome. 11. The wavelength of one of the spectral lines of helium is 492 nanometers. What is the energy of a photon with this wavelength? So, the energy of a photon is going to have to be, so the way to calculate energy, it's either the Planck's constant h times frequency, or if you don't have frequency, but you know the equation c, speed of light is equal to frequency times wavelength. So frequency is this, wavelength is lambda. So c, which is speed of light, is equal to frequency times lambda. So if I don't have frequency, I can say that energy is equal to h times a manipulation of this equation, which is, to solve for frequency, is c over lambda. Okay? So that's another way I can solve it. So you don't have to memorize Planck's constant or even c. Yes, ma'am?
What is the first equation? C equals what?
Frequency times wavelength. And what?
What is that symbol for frequency?
I forgot what it's called.
Can you just draw it bigger? Sorry. Oh, okay, V.
Yeah, it's like a cursive V, and lambda is this one. Or you can say frequency times wavelength. So it gives you the h is Planck's constant, and it gives you, and it's given to you in the constants table, Also C, which is speed of light, is given to you in the constants table. So you don't even have to memorize them. But you can round this up to 3.0 times 10 to the 8. So it's in the constants table. Is H and C, which you need. Okay. So what you're going to have to do is energy is equal to H, which is 6.626 times 10 to the negative 34 joules times second, multiplied by C, which is the speed of light, 3.0 times 10 to the 8th meters per second, over lambda. Lambda is the wavelength, but the wavelength is given to you in nanometers. You have to convert it to meters because speed of light is in meters per second. So 492 nanometers times, in 1 meter, I have 1 times 10, in 1 nanometer, 492 nanometers. In 1 nanometer, I have 1 times 10 to the negative 9, so 9 nanometers. Which means that I have 492 times 10 to the negative 9 meters. Just for simplification purposes. If you want to convert it to scientific notation, it would be 4.92 times 10 to the negative 11. Excuse me, times 10 to the, so you add 2, so 10 to the negative 7. But you don't have to do that if you're confused, because you can just plug this into the calculator. Meters. So when you plug this in, you should get an answer in joules, which is, oh, and one more thing. When you're plugging this into the calculator, use the parentheses so you don't get confused. So it's not, using order of operations against you, basically. So parenthesis 6.626 times 10 to the 34 negative times 3.0 times 10 to the 8th divided by 492 times 10 to the 9 negative. And you should get an answer of 4.04 times 10 to the negative 19 joules, which is D for this one. So this one, this one. All right, ignore number 12 because it's not accurate, so ignore it. Yeah. Yep. Has to be meters. Yeah. Has to be meters because the units cancel out. So meters and meters cancel out. Seconds and seconds cancel out. So that's why you're only left with joules as your answer. Okay. Ignore number 12. Let's move on to number 13. Ignore that. I think I copied and pasted accidentally. So, which of the following gas phase ions has the largest number of unpaired electrons in its ground state? So, you are looking for the largest number of unpaired electrons. If unpaired electrons, the way you know that is using electron configuration. So, you have to see the electron configuration of each of these and see which of them has the largest number of unpaired, right? So if you look at electron configuration, the things that are paired are going to look like this. So this means paired. And another way of saying that all the electrons are paired is calling it what? Diamagnetic. Correct? But if it's non-paired, like this only, if I have unpaired, I end up with a paramagnetic. So I have to look at the electron configuration. So I have chromium 3+. By the way, these are all ions. If they have 2+, 3+, whatever. When I say plus, that means I am losing electrons, correct? So chromium 3+. So if I look at the periodic table, chromium is right here. And for these transition metals, remember, you're not removing from the D at all. You're removing from the S first, right? So you always remove from the S first, and then if there's more to be removed, go to the D. So chromium 3+. So if we look at it, I recommend just using the noble gas configuration because it saves you a lot of time. So go to the last noble gas for chromium. So chromium is right here. The last noble gas is argon. So you're going to say argon. And then argon is in the 3. So I have 4s2. So I'm just going to look at the configuration of chromium on its own and then remove the electrons as we go. And then I always go 1 down for transition. So even though this is 4, transition begins at 3. So 3d1, 2, 3, 4. 3d4. And if you recall, chromium is one of the exceptions where if you're doing the electron configuration, you're going to have to give the D a priority and make it D5 and 4s1. If you don't remember that, that's okay. You don't even need it right now. But, so it's chromium 3+. That means I have to take away 3 electrons. So I take the first 2 from the S first, and then the second one I take from the D. So it's going to be argon 3d3. Because the D has, so in any D level, I have 1, 2, 3, 4, 5. Technically, this is what it's supposed to look like because it has 10 total electrons possible. 3d3, I always have to fill up all the ups first before I go back and fill the bottoms. So when it says 3d3, that means I have 3 unpaired. Okay. Let's look at cobalt. Cobalt 3+ is going to be, where's cobalt? Right here. Okay. So again, it's going to be argon, 4s2, then I have 3d, 1, 2, 3, 4, 5, 6, 7. It's 3+, that means I have to take 1 from here, and then 2 from here and 1 from here, so 3d6. So argon, 3d6. But because I have 3d6, that means I filled up all 5 ups and another 1 bottom. So that means I have 4 unpaired. So the way you draw is this. So 1, 2, 3, 4, 5. So here I have 1, 2, 3. Here I have 1, 2, 3, 4, 5. I have 1, 2, 3, 4, 5, 6. So I have 1, 2, 3, and 4 unpaired. Here I have 1, 2, 3 unpaired. Okay? So you have to fill all the ups first before you go back and fill the bottoms. Nickel 2+. So nickel is the one after argon. So argon, after cobalt. So 4s2, 3d8. Again, I want to make it 3. It's 2+. So I'm only, if it's 2, so since it's 2+, I'm only taking away from the 4s2. So now I have argon, 3d8, and again, it's going to look like this. 1, 2, 3, 4, 5, 6, 7, 8. So I only have 2 unpaired. What about copper? So with copper, it's going to be, again, argon. It's the one after nickel, so 4s2, 3d9. And I'm only taking 2 away, so just the 4s2. So it's going to be the configuration Ar3d9. Again, I have 5 orbitals. 1, 2, 3, 4, 5, 6, 7, 8, 9. I only have one unpaired. The question is asking for the largest number of unpaired. The largest number of unpaired here is 4. So I have 4 unpaired electrons for cobalt 3 plus. That means B is my answer. So the way to solve this one, you have to write down the electron configuration and see the largest number of unpaired based on how the electrons look like if you draw it. Okay? And the way you know that there's 5 here is because in the d orbital, in the d subshell, there's 5 orbitals. And again, each orbital can hold up to 2 electrons, one up, one down, which is the positive half spin, negative half spin. Okay? This is more chapter 9, chapter 8, electron configurations. Okay. Number 14, the diagram is missing, so this is what it should look like. So it's missing from your papers because it did not let me add images, but this is what it looks like. So you have a Lewis structure of this thing called for medinium ion, and it's asking for the geometry. Usually when it's asking for geometry, it's asking for molecular, because geometrical geometry is the one where, you know, it's not going to matter how many bonded or how many lone pairs you have, but molecular is the one where it matters. So there's a really nice diagram here that I like to use. If you want to take a picture of it, go ahead. It's also in your book, I think, of molecular geometry. So this is what it looks like. Okay, so it's asking you for A and B. There's A and B. And it's looking at the nitrogens. It wants it of the nitrogens. And they have nitrogen A and nitrogen B. So let's kind of separate nitrogen A and see what it looks like, and nitrogen B. So you have a nitrogen. So let's say A. You have a nitrogen. There's a double bond on one side to the C. Then there's a bond to the H and another bond to the H, and it's positively charged. The second one looks like this. It's single bonded to an N, to a C. There's 2 lone pairs. There's a hydrogen and another hydrogen. Okay. So let's look at it. The first one, what you're looking at is the what they call electron regions or electron density regions. Yes? Zoom in. Sure. Sorry. So let's look at A first. I'm going to do like a separation line. So in A, you are going to have, let's see how many electron density areas I have. So I have 1. Electron density areas are either bond or lone pairs. Either work. So here I have 1 bond, a second bond, and a third bond. Even though this one is a double bond, it's still considered 1 electron density area. So I have 1, 2, 3. Do I have any lone pairs? No. Oh, you can't see that. Okay. 1, 2, 3. Right? So I have 3 electron density areas, all bond pair. So 3 bond pairs, 0 lone pairs. According to my diagram, this fits into trigonal planar. So that means the N in A is trigonal planar. Let's look at B. B, I have 1 bond, 1 bond, 1 bond, and a lone pair. Okay? So I have 3 bond and 1 lone pair. According to my diagram, this fits into trigonal pyramidal, where I have 1, 2, 3 bonds and 1 lone. So this one would be trigonal pyramidal. So according to my answers, this would be B, where geometry at A is trigonal planar, geometry at B is trigonal pyramidal. So again, it's all based on the electron density areas. And then don't let this plus sign fool you. It means nothing. It just means it's positively charged because there's an extra electron. Because nitrogen is in group 5, which means it can only form technically 3 bonds to reach its octet. But here I have 4. So that's why it's showing you like the positive charge kind of cancels out the extra bond that it has. Okay. All right. So what is the geometry of SF4? So SF4 is going to be, so the first step to figure this one out is you have to draw the Lewis dot structure. So the Lewis structure. So to draw the Lewis structure for this one, you have to first calculate the number of electrons that you have. So for a number of electrons, S is in group 6, so it has 6. Plus I have 4 times F, which is in group 7. So 28 plus 6 is 34. So I have 34 total electrons that I'm supposed to have in this Lewis structure. So obviously, since I only have one S, it's going to be in the middle. S is one of my exceptions that can exceed the octet. So it can have more than 8 around it. I have 4 Fs. So I have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So far I have 2, 4, 6, 8, plus 6, 6, 6, and 6 is 4 times 6, which is 24. 8 plus 24 is 32. That means I am missing 2 electrons. I'm going to add them on the S because it can exceed the octet. So now I have 1, 2, 3, 4, 5. 5 electron density areas. 4 of them are bond pairs, and 1 of them is lone pair. If I go to again here, I have 5 electron density areas. 4 of them are lone pairs. 1 of them is bond pair. Excuse me, 4 are bond, 1 is lone. So it's going to be seesaw, which is C. Okay, so it's C. Saw. Number 16. How many sigma and pi bonds are in 1,3-butadiene? So a single bond has sigma. A double bond has 1 pi and 1 sigma. Okay? So let's see. So here, what you have to do is kind of draw it out even more. So it's going to be C with 2 H's attached to it, so don't forget those. Double bonded to a C with an H. Single bonded to a C with an H. Double bonded to a C with 2 H's. So now let's see how many sigma and how many pi. Here I have a sigma because it's single. Sigma. Here I have 1 sigma and 1 pi because it's a double bond. Sigma, sigma, sigma. Here I have sigma and 1 pi. Sigma and sigma. So let's count. I have, how many sigmas do I have? I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 sigma. Okay. 9 sigma. And I have 2 double bonds, so I have 2 pi's. So the answer is C. Okay. Let's do number 17. A 20-gram sample of mercury 3 oxide is heated strongly, causing it to decompose to a metallic mercury and O2 gas. What volume of O2 gas is produced measured at STP? So you have 20 grams of mercury, 3 oxide, which they give you, it's HGO. And the molar mass is 216.6. Heated strongly, so you have HGO. Anytime something is heated, it gives you O2 gas. Sorry, it's heated to decompose. So it gives you O2 gas and Hg. So it's asking for the volume of a gas that is produced. So first you have to kind of balance the equation out. So you have O2 gas, you only have one O here. So you're going to have to put 2, and you're going to have to put 2 right here. That's how it's balanced, right? So that's how it's balanced. So you have 20 grams, and you want to figure out the volume of O2 gas. The first step is you're going to have to find the moles of O2 gas, okay? And to figure that out, you have 20 grams of the whole thing. You're going to convert that to moles, so 1 mole HGO has 216.6 grams. 1 mole HGO has, 2 moles, HGO, according to my formula, has 1 mole O2. So from there, I can figure out how many moles of O2 I have in that sample. So 20 divided by 216.6 divided by 2 is 0.046. So I have 0.046 moles of O2. Now, they tell you it's a STP. STP means standard temperature and pressure. Standard temperature is going to be 0 degrees Celsius or 273 Kelvin, and standard pressure is going to be 1 atmospheric pressure. What equation do I know has moles, temperature, and pressure? PV equals nRT, right? It's asking you to find the volume anyway, so it's perfect. R is a constant. It's 0.0821. The temperature, again, is given to you because it's standard, and the pressure is given to you because it's standard. N is what I just solved for, which is the moles. So I'm solving for V. V equals nRT over P, which is 0.046 moles times 0.0821 times 1. The temperature, is 273 Kelvin over the pressure, which is 1. So V is equal to this. .03 liters is the answer. Yep.
Further question on that, why is it 9 instead of 7?
Let me flip. Because each double bond also has a sigma.
Yeah, but
So I have 1, 2. So you have to remember to draw the H2 into an H and an H. And here it's also an H to an H. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have to I would recommend separating it out like that. So now you have 1, 2, 3, 4, 5, 6, 7, 8, 9. Good? So this one is 18. When 30 milliliters of 0.10 mole AgNO3 is added to 30 milliliters of 0.10 moles NaCl, aqueous NaNO3, and solid AgCl are formed, how much solid AgCl is produced? So this one, all it's asking for is limiting reagent, basically. Excuse me, not limiting reagent. It's a molarity type of equation, okay, type of problem. So the equation that we have is M1 V1 is equal to M2 V2. Or we know that big M, or molarity, is equal to moles per liter. So it says 30 milliliters of, so you have 30 milliliters of 0.10 molar AgNO3 and 30 milliliters of 0.10 molar NaCl. These two are added, and I get aqueous NaNO3 and solid AgCl. So actually I was correct at first. This is a limiting reagent type of equation. So even though they give you milliliters and molarity, you can easily solve for moles, correct, using this equation? So they give you molarity, they give you milliliters. You just have to convert milliliters to liters and then solve for moles by multiplying the M and the L. So with this one, I'm just going to kind of scoot up a little bit. With this one, what you're going to do is you have 30 milliliters, which is basically divided by 1,000 is 0.03 liters, 0.03 liters. So the moles of AgNO3 and the moles of NaCl is what you're trying to find first, because the equation is something that looks like this. NaCl gives you because this is literally what it said in the equation. This plus this and this are added, they give you this and this. And it wants moles of this. So the moles of AgNO3 is equal to the molarity times the liters, based on this equation. So 0.03 times 0.10, 0.003, and here it's also going to be 0.003 moles. Okay? So yeah, you're given this. So it won't matter at this point because it's all kind of 1-to-1 ratio, but what you end up getting is another, so because it's all 1-to-1 ratio, this one's not really a lot of work. It's all 1-to-1 ratio. It's given to you in moles, so you don't even have to find limiting reagent. So you have 1 to 1 to 1 to 1. So I'm given 0.003 moles of this, 0.003 moles of that. That means I'm going to get 0.003 moles of the product, correct, based on the 1-to-1 ratio. So my answer is going to have to be A. So it's just understanding ratio. All right. Let's try number 19. Okay. So you have about 40 minutes, and I have more questions. Some of them, the concepts just repeat, so we have 40 minutes. So I'm going to try to see which ones are kind of different and go over those, and the rest you can kind of figure out on your own. I'll post the answers, and I'll show you them at the end as well. But let me see kind of which ones are different. So we already did, so 20 is similar to 1, to question 1, same concept. Okay, let's just go through and see how much we can get through. Okay, number 19. How much SrOH2 times H2? So whenever you see this, that means it's something that is wet. It has H2O inside of it. Okay. So it's needed to prepare this amount of solution in which whenever it's this, that means concentration. This means concentration. So the concentration of OH is 0.1 molar. So this one, all you have to do is, because you have milliliters and you have molarity, you can easily solve for what? For moles, correct? Because M is equals to mole over liters. You're just going to convert this to liters, which is 0.25 liters. And you have the moles. You can just, and you have the molarity, so you can just solve for moles. And when you solve for moles, you can easily convert to grams and then get the answer. So 0.1 times 0.25 gives you moles, which is equal to 0.025. And then to convert from moles to grams, you multiply by the molar mass. So 1 mole has 265.76 grams. And it's equal to 6.64, which is B. That's grams. Okay. So I'm going to skip over number 20 because we kind of went over it. It's the same concept as question 1, where you're trying to find the empirical formula based on the masses. Here it's giving it to you in masses. The other one gave it to you in percents, but it's the same concept. 21 is asking for which of the following is a non-electrolyte. A non-electrolyte in an aqueous solution. So a non-electrolyte is something that is not a strong acid or strong base and not a salt. So the first one is a strong acid, so it is an electrolyte. Electrolyte is something that dissociates 100% when added in water. Non-electrolyte is something that does not dissociate 100%. NaC2H3O2 is a strong also acid, and K2CO3 is a salt. So the only answer is CH2O, because this one is a molecule with carbon, hydrogen, and oxygen, which means it's a covalent molecule. A covalent molecule does not dissociate in water. So this one is going to be your answer because that's why it's a non-electrolyte. The others were either salts or strong acids or strong bases. So this one is D. There's another 21. So the other 21 says you have 40 milliliters of 0.2 molar aqueous NaOH added to 200 milliliters aqueous of 0.1 milliliter aqueous this in a flask at 25 degrees Celsius. Neglecting the effects of dilution, what is Q for this reaction? So this one you are solving for Q. So let's write down the overall equation that they tell us in the problem. So you have NaOH aqueous plus NaHCO3 aqueous, and it gives you something. And they're asking for Q. But they're asking for Q based on the delta H of these. So for this one, what you're going to have to do is do a double dissociation, see which one of them is basically a solid at the end, because they're both aqueous. So you're going to do, so this takes into consideration solubility rules and figure out the net ionic equation, adding the things up from the net ionic equation, and that would give you Q. So NaOH aqueous plus NaHCO3 aqueous. So to do a double dissociation, you're going to substitute this one with this one. So this one and this one go together. So again, you get NaOH. NaOH has Na, which is a group 1 element, which automatically makes it aqueous, right? The second one is also NaOH, Na, and the second one is HCO3. They go together. Which is also aqueous. Right? So they are both aqueous. They give you the same thing, actually. So you're neglecting the effects of dilution. What is Q for the reaction? So because, again, you have milliliters and moles, you are going to have, you can easily calculate the moles. So you have, this is going to be 0.04 liters. This is going to be 0.2 liters. So 0.04 liters times 0.2 m, again, gives you moles, which is 0.04. And then 0.2. Okay. So this is the moles of each that I have. So what you have is, it's giving you the kilojoules per mole of each of these. If we use the net ionic equation for this one, all of them are going to cancel out, right? Because they're all aqueous. There's no solid. So we can't use this method anymore. So the next method that we're going to have to use is look at these numbers that I have right here and use them in and use the moles that I have and then calculate the Q. So actually, you don't learn this in Chem 1. You learn this in Chem 2. So I'm going to skip that one. Skip the second 21 because it's Chem 2. I just realized that. Okay, skip that one. It's Chem 2. Because you have to use something called an ice table, and you learned that in Chem 2, so ignore that one. Sorry. Okay. In a well-insulated vessel, 50 grams ice at 0 degrees Celsius is added to 350 grams water at 32 degrees Celsius. What is the final temperature when the mixture reaches equilibrium and it's asking for and it's telling you that the heat of fusion is this? The reason it's giving you heat of fusion is because it starts at 0 degrees. So anytime we reach a temperature where it's a melting point or a boiling point, we use something called heat of fusion. Okay? So it's starting at 0 degrees Celsius, which is the melting point. And it reaches 32 degrees Celsius. So you have to, besides using C, which for water is 4.18, you're going to use the heat of fusion, which is, they give you, is 334. Okay? So whenever you're doing heat of fusion, or whenever you're doing a question like that, what happens is, it's kind of like, if I draw a graph, you have water starting at 0 degrees Celsius, and it goes up, and it reaches 32 degrees Celsius. And then it would probably go up more. But what I'm trying to calculate is how the Q in this whole entire thing. So what you're going to, oh no, it's not asking for Q, excuse me. It's asking for the final temperature. When it, oh, never mind. This is going to be, but this is what you would use if, let's say it was the same thing and it went to both. But here you actually have two different things. You have a well-insulated vessel of 50 grams ice. So you have 50 grams ice at 0 degrees Celsius. And you have water. So you have two different things. 350 grams H2O at 32 degrees Celsius. But even though you would technically use Q, you're basically having Q equals MCAT of the ice equal to Q over MCAT over the water. So this is kind of like a coffee cup calorimeter type of equation, type of problem, where you do Q of, for example, the ice is equal to negative Q of the water. Right? So Q1, that is, so heat that is lost from one system is absorbed by the surrounding. So you would use that type of equation. So you have Q1, which is going to use the ice. So we're going to make Q1 the ice. So 50 grams, because M. Here, instead of the C, which is 3.1, which is 4.18, you would use the 4.18. And delta T. So because in coffee cup calorimetry, they both reach an equilibrium temperature of a final T. So that means the TF is the same for the ice and for the water. So they kind of equal each other out. So the TF, the final temperature is going to be the same for both. So I'm looking for TF. So I have one variable, but on both sides of the equation, basically. So TF minus 0 degrees Celsius. But because this right here is at 0 degrees, I'm going to take into consideration fusion. So to take into consideration fusion, I will convert the grams into moles and add it to where it's N delta H of fusion. So N is, or actually no, just multiply it by the H, you can multiply the grams. So mass times H of fusion, which is the 50 grams times the 334 joules per gram. Because again, this one is at 0 degrees Celsius. You have to take into consideration fusion. And then you equal to that. Always put the minus on the outside and put everything else in parentheses so you remember that the minus is distributed on everything, basically. So here it's, again, 350 grams times C, which is 4.18, times TF, which is the final temperature that it's trying to reach. Also, you know, because this one's starting at 0 and this one's starting at 32, you know the temperature that it's going to reach is going to be somewhere in the middle between 0 and 32. But because I have more water, it's going to be closer to the 32 than to the 0. So TF minus, again, 32, because 32 is initial. Right? So what you end up doing is you have 50 times 4.18. So you have 209 times TF minus 0 plus the 50 times 334, which is 16700. This is from that. Is equal to negative the 350 times 4.18 is 1463 times TF minus 32. So you're going to distribute it like this. So 209F TF minus 0, because 0 and 209 multiplied is 0, plus 16700 equals negative 1463 TF plus, so 1643 times 32 minus, that's why you get the plus, is 52576. Okay? So now you want to get all the variables with TF on one side and all the numbers on one side. So if I get the TFs here, if I add this one here, so plus 1463 TF, so 209 plus 1463 is 1672. TF is equal to, if I subtract 16700, so 52576 minus 16700, which is 35876. To find TF, you divide both sides by 1672, and TF is equal to 21.4 degrees Celsius, which in my answers is oh wait, no. Yep. So the closest one here to 21.4, so I guess it would be a rounding error of some sort, is answer C. You got 18? By dividing this? Oh, okay. Oh, okay. Well, the answer is 18 actually. Yeah. But I got 22. Yeah, you're right. Wait, let me check. Make sure that you are. Yep. Okay. Sorry, I read the answer before. So the answer before is the one that's. So it's 18. That's the answer. So the trick here, that makes more sense. 4, 6, 6. Yep. Yeah, my mistake. 21 is the one that's C. Excuse me. So it's 18. So the trick to this one is knowing that because it's at 0 degrees Celsius, it starts at 0 degrees Celsius, you're going to have to use the heat of fusion multiplied by the grams on the side of the water, on the side of the ice. So that's the trick to this one. Because if you forget this, you're not going to get the correct answer. If you forget this part, you're going to get a completely different answer. If it's not at 0 or 100, you don't have to use this concept. Okay, 23. 24, ignore. It's again Chem 2. Okay, so it's telling you that the bond association enthalpies of the H to H bond and the H to Cl bond is this. And this, respectively. So H to H is 435 kilojoules per mole, and H to Cl is 431 kilojoules per mole. And the delta H of formation of HCl is negative 92 kilojoules per mole. It's asking for the bond dissociation enthalpy of the Cl to Cl bond. Okay. So, okay. Huh. This one is also chem 2. Wow, okay. I guess I did not look very closely at these. Ignore 23. It's also chem 2. I apologize. I guess I forgot to look over this a second time. Huh? Yes, but you had this in where if you had, let's say, HCl plus something gives you something plus something, and then that's what I thought. That's why when I saw this problem, I put it on here, but then when I read it again, this is the one where let's say you do the all the delta H's of the reagents, or excuse me, yeah, of the reagents minus the delta H's of the products, the sum. Right? That's this type of problem. But this one is different. I looked differently at it. I apologize for that. But that's the one that you would use. So this one, it's fair game, I guess, this one. And then you would do delta H of the reagents minus delta H of the products of the sum of the delta H of formations, which they would give you the bond energies of. Okay. Skip over to 25. I'm trying to see how much time we have. We have 15 minutes. So let me see which ones are different and go over them. So 25. Oh, okay. Let's do 25. It's kind of like a balanced. Oh, it's balanced. Okay. It's asking for the ratio of the coefficient of ClO2 to ClO3 minus. So ClO2 is right here. This is supposed to be an arrow. So this is balanced. It's telling you that it's balanced, but if it wasn't balanced, you would have to balance it. And it's asking for the ratio of the coefficient of ClO2 to ClO3 minus. So ClO2 to ClO3 minus is 1 to 1. So the answer would be A. Oh, no, it's not balanced. It says when the equation is balanced. Sorry. So let's do it again. So you have ClO2 So you have ClO2 and OH minus. Oh, plus H2. Okay, so you have two H's on this side, only one H on this side. So you would have to add one. Always O. For these, when you balance the C first, then the H, then the O. So all the C's first. So you have one C here, or excuse me. Oh, it's Cl. So you, whatever, C or any other element, then the H, then the O. So here you have Cl. You have one here, you have two on this side. So you have to add a 2 here. Then you have two Cl's, one Cl, one Cl, so Cl's are perfect. Then you have H's first before the O, because O's are on everything. You have one H here, you have two H's here, so you'd have to add a 2 here. So now I have 2 O's, 4 O's, because 2 times 2. Then here I have 2 O's, and 3 O's, and 1 O. So I have here 6 O's total. Here I have 2 plus 3 is 5 plus 1, so I have 6 O's, so the O's also balance out. So now that's the balanced equation. So it's asking for the coefficient of ClO2 and ClO3 minus. So here I have a 2, here I have a 1, so the coefficient, the ratio of the coefficient is going to be 2 to 1. Okay? Okay. 26 is more on the conceptual side. It says, which of the following statements is best supported by the data from the Rutherford's experiment of scattering alpha particles within a thin metal foil? So let's read the answer choices. So it says the mass and positive, so the Rutherford experiment is the one with the gold foil, where it discovered the positive, basically that there's electrons around it. And that there is a positive, so it discovered, so it's the one where you have a gold foil and there was something shine through it, the alpha particles, and it basically showed the scattering of these alpha particles, showing that there is going to be a positively charged center. So based on that, let's read the answer choices. So it says the mass and positive charge of an atom are concentrated in its center. Electrons in atoms occupy only certain specific energy levels. Moving particles can also be described as waves, and atoms of a given element do not have the same identical masses. Well, it says that it's alpha particles. Also, it's the Rutherford experiment, which dealt with basically seeing that there is a positively charged center, which is called the nucleus of an atom. So A is going to have to be the answer for this one. You can also use process of elimination because the last couple ones don't make sense. Okay. 27 deals with periodic table trends. So it says as atomic number increases from 11 to 15. So if atomic number increases, that means I'm going this way. So if I'm going this way, what happens to the atomic radius? We said atomic radius this way is going to decrease. So 27 is going to be B. So periodic table trends was the one for 27. 28. Nitrogen has a greater first ionization energy than oxygen. What is the best explanation for this observation? So nitrogen has a greater first ionization energy than oxygen. The definition of ionization energy, again, is the amount of energy that is needed to lose an electron, right? So it's the amount of energy that is needed to lose an electron. So why would nitrogen have a greater, so if it has a greater ionization energy, that means that it's harder to lose electrons. So why would nitrogen be harder to lose electrons than oxygen? So let's find an explanation. So it says nitrogen is more electronegative than oxygen. A nitrogen atom is smaller than an oxygen atom. The electron ionized from nitrogen experiences less electron-electron repulsion than the electron ionized from oxygen. The electron ionized from nitrogen is a 2s electron, while the electron ionized from oxygen is a 2p electron. So the answer for this one is gonna have so this is A, B, C, and D. So the answer for this one is actually C, that the electron ionized from nitrogen experiences less electron-electron repulsion than the electron ionized from oxygen. So if it experiences less repulsion, that means that it's more attracted. And because it's more attracted, there is a higher ionization energy. Because even though A is kind of like, A sounds like a good answer, because it would be a good answer, but in actuality, oxygen is more electronegative than nitrogen. So it can be the answer. So A sounds like a good answer, but it's not, because oxygen is more electronegative. But the answer is because the repulsion, when the repulsion is great, the ionization energy is going to be lower. That means it's more likely to lose the electron. But when the ionization energy is not great, it's basically when the repulsion, is very little, which means its attraction is greater, the attraction is going to make it less likely to lose this electron. So that's why ionization energy would be higher. Okay? Okay, let's do 29. Which set of quantum numbers N, L, M, L, and MS is invalid? So the trick to that one is, if you look back, we said that N, we have L, we have ML, and we have MS. N is any number. L can only go from 0 to N minus 1, which means that L can never be equal to N and can never be greater than N. ML can only go from negative L to positive L, and MS is either positive half or negative half. So you're really looking at either one where L and N are the same, which means it cannot exist, or one where you have ML, something not in the range of negative L to positive L. So if you look, the only one that doesn't fit, the one that has something that is invalid is going to have to be A. Because in A, N and L are the same number 1. And that can't happen. So we said N and L can never be the same number. L can only go from 0 up to N minus 1. Okay? So N can be, if N is 5, L can go 0, 1, 2, 3, or 4, but can't be 5. Okay? 30 is polarity. Which molecule is nonpolar yet contains polar covalent bonds? So the way to determine something to be nonpolar is one, so if it's nonpolar, it's one where the central atom, let's say X, does not have lone pairs on it, and where the elements around it are symmetrical. So let's say this is A and this is also A. Even though both of them are going to have a pole, it's going to be an equivalent pole. So even though there is a polar bond between X and A and X and A, but because they are symmetrical, they are going to cancel each other out, and it has a net dipole moment of 0. So a net dipole of 0, making it nonpolar overall. So in these, so B won't work because even though C is a central atom, N and H are not symmetrical. NH3, N would look like this. So it would have 3 bonds to NH, but it would have 2 lone pairs on top of it, so it wouldn't work. And P4 is only one element, so it also wouldn't work. So the only one that makes sense is CO2, and CO2 would look like this. So C can form 4 bonds, and because it's 2 oxygens, it's going to be double bonded to the O and double bonded to the other O, because also oxygen wants to form 2 bonds. And even though they are both have polar bonds, they are symmetrical, so they have a net dipole of 0, making it nonpolar, and there are no lone pairs around the C, which is the central atom. So another thing that shows you that it's nonpolar. Okay. So we have about 5 minutes, so I'm going to kind of run through these. Number 31. It says the nitrite ion, NO2 minus, can be represented as a resonance hybrid of 2 significant Lewis structures. Which statement about these is correct? So you have to first draw the Lewis structure of NO2 minus. So you have N, which has 5, plus 2 times 6, plus 1, because it's a minus. So that's 12, plus 5 is 17, so you have 18 total electrons. So it's going to look like this. You have an N. Start out with an O, so you have 1, 2, 3, 6 and 6, 12, plus 4 is 16. Okay. So it's going to look like this. Or if you want to draw, say 2, 4, 6, 8, 10, 12, 14, 16, 18. Or the other resonance you can draw is you can draw a double bond to one of them. or you can draw a double bond to the other one. So these are 3 resonance structures, but the ones that are the, yes?
Why aren't there lone pairs on the bottom 2 ends? Is it because the lone 2 pairs were taken away?
Why aren't there lone pairs? Or why are there?
Why aren't there?
Wait, let me count. 2, 4, 6, 8, 10, 12, 14, 16. Yeah, no, there's 2. There are. Sorry, I forgot them. But you can either draw it like that, but this one has the worst formal charge, right? So the one that has the best formal charge is the one where you have double bond O's. But because with resonance, it means that you can move the, so these are technically all resonance. Resonance means that you move the electrons or you move the double bonds because the double bonds are indication of electrons. So the question is asking, which 2 statements about this are correct? The 2 resonance structures contribute equally to the structure. The formal charges of nitrogen is 0 on both resonance structures. So let's look at the formal charges of nitrogen. Here it's 1, 2, 3. So formal charges is lones, or I call it dots plus lines. So here I have 1, 2, 3, 4. So you have 5 minus 4. So it's, it's the valence electrons minus dots plus lines. So here it's 5 minus 4, which is 1. Here it's 1, 2, 3, 4, 5, which is 5 minus 5, which is 0. So this is looking at 31. And also here it's 1, 2, 3, 4, 5 minus 5. For this one, because it's asking for 2 significant Lewis structures, you're going to look at the ones with the best formal charge, not the first one. The first one is not going to count. So for this one, since both of them have a formal charge of 0 on the nitrogen, both one works because both of them contribute to the structure equally. And the second one says that the formal charges both are 0. This one, the formal charge would be 1, and that's why we're not even considering it one of the resonance structures because it says 2. If it said maybe like use all resonance structures possible, then this one wouldn't count, or would count. But here, C would be the answer. Okay. What is the molecular geometry of IF3? So I is in group 7. So we have 7 plus 3 times 7, which is 21. So you have 28 total electrons. So if I were to draw IF3, it would look like this. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 18, 20, 22, 24, 26, 28. So when it's asking for the molecular geometry, I have 5 areas of electron densities. So 1, 2, 3, 4, 5. 3 of them are lone pairs, are bond pairs, excuse me, and 2 of them are lone pairs. So that brings me to the shape of T-shaped. So it's C, according to the paper, which is right here. So T-shaped is the one where you have 2 lone and 3 bond, which is what I have right here, 3 bond and 2 lone. Okay, which contains sp3 hybridization carbon atoms. sp3 hybridization is ones that are that have basically 4 bonds around the central atom, or 4 electron density areas, because it could be bond pairs or lone pairs. So benzene, C6H6 is going to be, it's asking for the carbon atoms. So it's going to be C with C6, 1, 2, 3, 4, 5, 6. And it's going to have 6 H's. So a lot of these are going to be double bonded. And it's going to be double bonding here. So H. 3, 1, 2, 3. So it's going to have 1, 2. So it's going to look like that. So here, as you can see, every C has 1, 2, 3. So when it has 3, it's only sp2 hybridized. In order for it to have an sp3 hybridization, it has to have 4 bonds around it. So let's look at B. B is going to look like this. So you have a C. So this is A. B is going to look like this. C to a C, right? Then I have 6 H's, which means I'm going to have 1, 2, 3, 1, 2, 3. Here, as you can see, around each C, there's 1, 2, 3, 4. 1, 2, 3, 4, which means it's an sp3 hybridization. So B is going to be my answer. Okay. 34 is this is supposed to be a triple bond. Excuse me about that, and I'm going to do a different paper. But this one is going to be, so it's CH3, C triple bond, C, CH3. A triple bond has 2 sigmas and 1 pi. Okay? So let's draw it out completely. So you have a C, 1, 2, 3 H's, to a C, triple bonded to a C, to a C, 1, 2, 3 H's. Right? So now, let's look at how many sigmas and how many pi's I have. So I have 1, 2, 3, 4, 5, 6, plus a pi, 7, 8, 9, 10. Let me count that again. 1, 2, 3, 4, 5, 6, 7, 8. I think, okay, I messed up. I messed up. It's 1 sigma and 2 pi. And the double bond, excuse me. So it's 2 pi. So a single bond is sigma, 1 sigma. A double bond is 1 sigma and 1 pi. A triple bond is 1 sigma and 2 pi. So you always add in the pi, not the sigma. So now I have 9 sigmas, which is going to be C. That's my answer. So let me post the answer, the complete answer key here. And I'm going to, the ones that we did not go over, the ones that we kind of ignored, I'm going to also put ignore next to them. So number 23, also ignore. And number 21 is also ignore. Yes. Yes. I'll post it right after this. But this is the answer key. I think that's